Also, one more thing is to introduce various resource persons who are available within our reach, so to speak, so that interested students and teachers, they can contact them and pursue further studies and so on. So it helps them communicate with the resource persons available. So this kind of activity we expect from every developed university. You can see that happening in Europe and US and Canada, places like that. Unfortunately, it is not very common in India. Our universities are not geared up to this kind of activity, the so-called outreach activities. They're more they're buried in admissions and examination work, so to speak. So at least we are doing that for in the field of physics. At least we are very happy that we are able to do that. So today we have a distinguished scientist from Germany who is originally from India, who is now working in Germany. So I welcome him to this webinar. So he will be speaking on space radiation environment and its detection. So he will speak for about 15 minutes. Before I request him to speak, I request our Joint Secretary, Dr. Rudraswamy, to introduce the speaker briefly. Over to you, Rudraswamy.
Sir, thank you very much, sir, for extending this great opportunity. It is indeed a great honor and immense pleasure for me to introduce Dr. Shrinivasarao or Kulkarni, an eminent scientist and speaker of today's online talk. Dr. Shrinivasarao or Kulkarni obtained his PhD degree in the year 2005 from Bangalore University, published more than 100 research papers in international journals, served as a postdoctoral fellow in USA for the year 2007 to 2008, served as a coordinator for scientific activities of ISRO, served as a lead instrument scientist for the year 2009 to 2020 at the IEAP Germany, project manager for the year 2020 at IEAP Germany, co-investigator of energetic particle detector at Solar Orbiter ESA mission Germany for the year 2022, quality assurance manager of Ultrasat camera DESI and scientific staff at Levinas Institute for Astrophysics, Potsdam, Germany for the year 2023, and presently serving as a radiation assurance expert and quality assurance coordinator at Mynaric Lasercom GmbH, Munich, Germany. With this brief introduction, may I now request Dr. Shrinivasarao Kulkarni, an eminent scientist, to kindly speak on space radiation environment and its detection. Over you to Dr. Kulkarni, and thank you very much, sir. Thank you very much.
Okay, thanks a lot.
Okay. Shall
Okay.
I?
Yeah, please continue.
Okay. Thank you very much, sir. Thank you, Professor Kagli, Chairman, President of KPA, and Professor Rudraswamy. Thank you for a nice introduction. Thank you very much for giving an opportunity to deliver a talk in the KPA meeting. I will going to talk about the space radiation and its detection. I will go very briefly because what subject it is. Here I planned just introducing what is space radiation, especially cosmic rays and solar energetic particles. Just introduction with a little history. Then what are those things and what are the constituents of cosmic rays and solar energetic particles? How they interact means in basic interaction process. This is very, very important to understand how to detect them and what kind of materials is used for which very specific purpose. I mean specific kind of particle detection, and one of the technique which I involved in designing building and testing and all the activities, and it is landed on moon. This Chango 4 is a lunar neutron dosimetry system, and it's served its function for more than 6 months. So I'm going to discuss about that in another example. Okay, as we know, space radiation is very, very important because nowadays the communication through the satellite and all those things, and we know the radiation effects on the electronics devices. If any event happened in the stellar or solar regime, then there may be an effect on our satellites or electronic gadgets. These are surrounding our Earth. Hence, the understanding the space radiation is very, very important to how to um, design them and how to monitor all the activities. Here you see in the right corner top is the sun, and it's a tiny spot here, Earth. And sun is we know when it's active or even it's not active, is emitting the radiation in the terms of flares or CME, the cosmic and it's as plasma coronal mass ejection, CME, is consisting of photonic radiation and particle radiation. In other direction, so we see these red arrow spots is a cosmic radiation. These are the extragalactic origin. Here you see the lines. These are magnetic lines of the Earth. Due to the radiation pressure, they are distorted. If you go to the zoom, here we will see the right bottom corner, the Earth, and Earth, we know Earth is tilted, and there is a rotation axis and the magnetic axis, and around the sun, around the Earth, there is a magnetic belt. It's called as a radiation belt. It's called as a Valerian belt. These are very important because of Valerian belt and atmosphere, we are protected from the radiation. If there is no these magnetic structure around the Earth, and we will be, it's very difficult to formation of the life on the Earth. Here there are two kind of belts. One is inner belt and an outer belt. These formation due to the magnetic field and the charged particles emitted from the solar and galactic origin. They are trapped inside these belts or magnetic lines, and one called as inner belt and outer belt. You will see how we are going to measure them, what is the particles of these things, belts, in the coming slides. Just I will start with a brief introduction history. In earlier, before late 80s and early 90s, radiation was very, very hot topic. We know at that time, from history, the radioactivity was discovered, and many were thought that radiation from the Earth crust or something. In the meantime, there were balloon experiments were going on, and the Victor Hess is one of the main scientists at that time. He did several balloon experiments, and he noticed that, and also demonstrated that the radiation is not from the Earth crust; is from the outer space. As his experiment shows that as the altitude of his balloon or his experimental instruments rising, the radiation level also increases. Hence, it is understood that radiation is also coming from the outside, and he called it as a cosmic radiation. Later, it's called as cosmic rays. For that, he got the Nobel Prize. In the same time, after 3 decades, there were several experiments in India also carried out. We know our scientist Baba. He is one of the famous cosmic ray experimental scientist. He did several experiments. One of the famous experiment carried out Bangalore Central College in the late 40s with his co-worker, Professor A.S. Rao. They also demonstrated and also identified the cosmic radiations from the outer surfaces and published the work. At the same time, later, a team led by Baba and Srikantan, they have installed a muon or neutrino detector in the KGF Kolar Goldfield to detect the cosmic rays, especially neutrinos and muons. It is also very famous experiment, and also there are several people at that time and also working like Baba, Vikram Sarabhai, Srikantan, Menon, and Kaushik. They contributed a lot in the initial days of the Indian cosmic ray experiments. And also one more very, very important experiment carried out in 1985, led by the Kaushik and his team, Professor Kaushik and his team. They designed an instrument called as Anuradha. It's an experiment to determine the cosmic rays, and it is launched he launched in the one of Space Lab 3 Challenger satellite, and it is at the altitude of 350 kilometers, and it was there nearly 2 weeks in the space, and detected several particles, charged particles, like anomalous cosmic rays and heavy ions cosmic rays. Anomalous cosmic rays, the origin is interstellar origin with less energy, and cosmic rays is the stellar origin and very high energy. And also they found the charged particles, heavy ions in the range of 10 to 50 MeV per nuke. These are the initial days. And recently, there are several experiments are going on to understand the space weather. Here, mainly, I am mentioning the only few space experiments or space instruments or space missions. Those are involved or already completed their work, or still some of them are working in space to determination or detecting the space radiation atmosphere or environment. Means space radiation environment means detection of the charge and charge particles and neutral particles to either density, energy, and type of the particle. Here we know Voyager 1 and 2. These are very famous two spacecraft. Already one of them crossed our heliosphere, and one of them at the edge of the heliosphere. They also have a detector system to detect the charged particles. Helios 1 and 2, led by the DLR German American mission, DLR and NASA mission. These are also there are particle detector system on Helios, and they were also detected and identified some charged particles in the constituents and their densities. And also SOHO. SOHO is a Solar Heliospheric Observatory. It's an ESA and NASA mission. Also, it has several, charged particle instruments and stereo. Also, it has a charged particle instrument. One of the instruments from the Kiel, where I worked in the group. They have contributed for this mission, and our mission as well as Chandrayaan also radiation dosimetry mission is responsible for the detecting the moon environment and its radiation dose. Chandra X-ray Observatory, name itself. Excuse me, it shows that the mission ends in 10 minutes. Can I restart?
No. It is not. No. It's not going to end. No, maybe recording. Don't worry about that.
Okay, fine. Chandra is a space observatory for it has also an particle detector system, and Fermi and Parker Solar Probe. And Solar Orbiter is a ESA mission. I also contributed. I was worked for a Solar Orbiter 2 instruments. I will going to show one of the results. It's a EPT, HET. EPT means electron proton telescope, and HET means high energy telescope. I will going to show in the next slide. And Aditya L1 and Proba also is a German mission, ESA mission, and so there are 1, 2, 3. There are 3 three mission launched, and they were had the particle detector instruments. And interestingly, the Proba 1 and 3 are launched by the PSLV. Then JUICE is a Jupiter icy moon mission. It's an ESA mission. There were particle instruments, and L5 is a mission for L5 Lagrange 5 spot mission. It's again ESA mission, and ExoMars. Yes, ESA mission. Actually, I started my career with ExoMars. Unfortunately, it's not launched yet, but it has a very beautiful radiation environment monitoring system or particle detector system. When I was working as a PhD student in ISRO or Bangalore University, there is a group by B.R. Bhatt. They were also doing a very interesting experiment called using their RADFETs. What they were doing, just they are installing the RADFET for the geo satellites or geo missions to understand the Van Allen belt, dose estimation, or just using the small small device called a radiation effect. These are all the missions or instruments, okay, involved in understanding our space weather. Then here is the one of the result of a solar orbiter. It has detected solar orbiter. It has detected the charged particles, electrons, protons, and heavy ions. Here is the one of the instruments, EPT, HT. EPT means electron proton telescope, and HT means high energy telescope. The solar orbiter was launched in 2020 February. Here, its detection, its functionality started in the early March and 1st of March. And okay, it's observing the solar radiation when it's moving around the sun. It's elliptical orbit, and here it started is in the early March, and outside peaks are the ions, inside peaks are electrons. Whenever it's moving around the sun, okay, so it's observing whenever the events appear, or sun is active or sun is okay. I can say angry. You can say you will see the some spike. Here's the ion spike, and okay, here ion spike in the month of May. And if you go to the June, there are very big event happened here. There are several kind of ions observed in the instrument. If you go to at the end of the cycle in the August, is here it has observed the electrons as well as ions. If you go to each orbit is a 6 months orbit, and if you go to the second orbit, the middle of the orbit, almost all, okay, middle of the orbit, sun is very, very active. Then we have observed intensity electron as well as the heavy ion intensities. Finally, it is okay. So understand the intensity of the particles and their different constituents. Then okay, I will go very quickly. What are the cosmic rays? The cosmic rays is okay. High energy particle outside the solar system. It may be due to supernova and other events, and mainly consisting of 90% of the protons and 9% alpha particles and 1% of
just excuse me 1 minute.
Yes, please.
What is happening is some problem, technical problem is there. After 4 minutes, 5 minutes, this will be switched off. So all of us have to join again. Again, a technical problem again. Please, you can continue for another 4 minutes.
No problem. So I will join again. Okay.
Again with the same link, please join.
Okay. Shall I join now?
Continue till the end. Break after. Okay. I don't know why it has happened. They are also puzzled.
Okay. No problem, sir.
They will restart. This has not happened before. First time.
Okay, no problem, sir. Yeah, fine. Yeah. So cosmic rays it's a very interesting topic, and also if you go to understand these cosmic origin, it's outside the solar system, and its energy and constituents or density of the particles. If you see the right side, there are several experiments conducted on the surface as well as the on space. Here, this gives the line gives the intensity of the particles in the space, and y-axis is the density, and x-axis is the energy in terms of GeV. It's enormous energy particles. It's 10 to 10 times to 12 GeV particles. Okay, but intensity is very, very less. For example, here you go to the isotope or Tibet experiments. Those are in high altitude, and in the Antarctica experiments, they have found very high energy particles in the space. And here there are some arrow mark. These are the arrow mark showing that where we can generate, and on Earth, using the accelerator facility, we can reach this kind of energy, not what they have shown here, what they have detected through their experiments at different locations. Means cosmic rays, natural radiation. If you go to the solar particles, its origin is sun. It's consisting of protons, photons, electrons, heavy ions. Photon means electromagnetic radiation, especially electromagnetic radiation is a flare. Flare is emitted across virtually the entire electromagnetic radiation, especially here's optical emission, X-ray and gamma. So these are we are interested. And second is the coronal mass ejection. This is a significant release of plasma and accompanying the magnetic field for solar corona. Means when the particles are ejected from the sun, so they are moving around the magnetic lines. Here there is one of the picture of the spacecraft. This is SOHO, I guess. What they did, they create the eclipse, means they prepare a disk like this to cover the sun, and only they will observe the flares and CMEs emitted from the sun. Yes. Shall I stop here and restart, sir?
Yeah. Just 1 minute. Let us. I'll just give instructions. So I request all of you to join again. This meeting will suddenly close after 2 minutes. Then again join with the same link. Some technical issue they are trying to rectify. So with the same link, please join again after now 1 minute. 1 minute 45 seconds. So I think we'll wait for that.
Better, sir. Okay.
Closure of the meeting, so that interruption better. So please, this unfortunately this has happened. Never happened before. Some technical matter.
Yeah.
So with the same link, again join, and let us continue from this point onwards. What are solar energy particles? Let us wait for the closing of the meeting, automatic closing, technical closing of the meeting.
Okay.
I don't know why it has happened.
Only we.
Yeah.
Okay. Only we discussed that.
Sorry for the inconvenience, sir.
I don't know what has happened. Okay. So you can. Okay, we'll join again. The same link, we'll join with the same link.
Okay.
Yes, sir, same link.
Same link, okay. Less than a minute left.
Yeah.
Okay, we'll count down. Begin the countdown. This has never happened. How many minutes? Less than a minute now. Okay. Less than, it will close automatically. Again, we have to join with the same link, please. So let us join. Unfortunately, some technical problem, which is 55 seconds. So it will close and then again join. Slowly this countdown is happening. Okay, please join. You have to be, who is the co-host? Again, we have to make host. Kulkarni has not joined, so we have to wait. Raman is the host, but speaker has to join. Kulkarni has joined. Please,
Okay, sir.
keep the host. Now who is the person? No. Okay. Now you can try to share the file.
Okay, sir. Okay, sir.
Once you are host, only you can share. Okay. Now please.
Yeah. Can you see it on my screen? Okay.
Not, it's coming up.
Okay.
Yeah. Fine. Okay. Now perfect.
Okay,
No problem. Please continue. Sorry for the interruption.
No problem, sir. Okay.
Okay, energetical particles.
Yeah. I was okay talking about these solar cosmic rays and solar energy particles. Yeah, what we know, these cosmic rays are consisting of charged particles, including the photons, and solar energy particles also consisting of the charged particles like protons, helium ions, and alpha particles, electrons, and heavy ions, as well as the photons
What is
like
the
X-rays.
percentage? If you don't, what is the percentage of composition? How much percentage electrons? How many percentage protons? Heavy ions?
I
Yeah,
mean,
some idea. Some idea
yeah,
you can
yeah.
give us.
Mainly the 90%.
Ah,
Protons and electrons are 90%, and
90%.
less than 10% is alpha, and okay, 1 or 2% are heavy ions.
Ah,
Similar to the cosmic rays, especially the solar energy particles. Okay, especially plasma is rich in protons and electrons, and some extent, okay, is helium ions. Mainly,
okay.
those are the main sources.
Yes, yes.
Particles. Yeah. Now we will go to the how to detect these things. To detect these things, we have to understand, okay, how they interact with the materials, or which, okay, detect the item we are using, the system we are using to, okay, so detect them. Then we will go with the one by one. I will go very quickly here, how the electrons and photons are interacting with the materials. We know where the gammas or X-rays, they are interacting with the material, especially any kind of material, through the three processes. One is photoelectric effect, Compton effect, and pair production. You know what is photoelectric effect? Photoelectric effect is an interaction between the photon and the innermost electron, and okay, ejection of electron means the whole process is nothing but the absorption of energy and in all these process. Okay, here in the Compton, is outermost electrons is freely, in generally called as freely, means it's a loosely bind electron, and scatters against losing the energy. The photon is interacting with the outermost electron. If you consider the pair production, it's a production of pairs of electrons, projectron protection when projectron when interacting with the nucleus of the atom. Here the cross section. Um, cross section. If you go to the cross section, as the energy and Z means atomic number. The photoelectric effect is dominant in the lower energy, and pair production is dominant in the higher energy. The Compton is in between. Okay, and this is the main principle to detection of the photonic particles. Electrons mainly interacting with the orbital electrons and the nucleus, and again it's elastic or inelastic. The basic phenomena is how what kind of energy is, how much energy is losing in their interaction. Similarly, if you're talking about the heavy ions is a little bit different, but okay, process is same, and interacting is charged particle interacting with the nucleus and the charge electrons, and it's losing energy, and it's as per this, we know where the Bethe-Bloch formula or Bethe-Bloch equation. It is the very famous equation. It shows that how the charged particles enter into the material, it loses its energy. It depends on its very simplified version is the d by dx is the energy loss in the system when entering, or when it's interacting with the material, as a function of its energy and atomic number and density of the material. Here I have shown how they are interacting. If you here I took a gold ion in the silicon. It's a simulation. It increases energy at a certain level, at a certain point. Its interaction is due to two process. One is electronic interaction and the nuclear interaction. This is a combination of these two. This is the combination of these two. Here is a nuclear interaction, it's electronic interaction, and it reaches the peak, and okay, it decreases as energy of the particle increases in the material. If you go to the neutron is philosophy is entirely different, because it's a neutral particle. Here we have to consider, okay, so, the head-on collision of the neutral particle with the nucleus, and how much energy is losing during its collision. in general, summarizing different particles like alpha, beta, gamma, and X-rays and neutron, we know the alpha we can stop because it's energy and it's a mass. We can stop, and heavy ion also we can stop. So it purely depends on the energy. It cannot penetrate a paper. Generally, paper is 80 micron thick. If it is a low energy, we can stop in the paper itself. Very high energy, it can penetrate. Okay, if it is a beta particle, it's a normal energy. It can easily be pass through the paper and it stops. Okay, it's in aluminum sheet or so. It depends on the energy. And X-rays, we know X-rays are okay. They can easily penetrate through the general X-rays with more than 200 keV. Gammas also, gamma already always find more than 500 600 keV energy, and they can easily pass through the thick aluminum sheet as well as the some high density material. Depends on against energy. But neutron is not like that. As they are neutral, they can easily penetrate without interaction with the material. Only we can stop with a high rich in hydrogen material like any polymer or water like that. Okay, that's why we are using the neutron in in the new reactor. They are using heavy water to stop the neutrons. Those are generated in the nuclear reaction. Here, summarizing, just I will go very quickly here because I want to cover interesting topic in the coming slides. We know photons, how they interact through the interact and lose the energy through this mechanism: photoelectric effect, Compton pair production, and photonuclear reaction, charged particles, light charged particles, and heavy charged particles. Again, elastic and inelastic process, and Bremsstrahlung or Cherenkov interaction or nuclear interaction. Nuclear interaction, it may be the different kind of nuclear reactions. And neutral particles, what I have mentioned for the neutron, is against elastic, inelastic, and hadron collision, fission reaction, and hadronic shower. These are the main principles behind in energy loss of all these kind of particles: neutral charged particles. And neutral means consisting of photon, electromagnetic radiation, and neutron-like particles, bosons, hadrons. Then, I will jump to the detection techniques. Here, I work for the detectors system for detecting the charged particles. Detection of the different kind of particles is not so easy because if you go for a space mission, they have given some baseline. Baseline means they have given some definition. We have to define. We have to detect kind of type of particles, and the energy range is from some level, from X to Y or something, some few keV to some GeVs, because to cover all kind of particles like X-rays, gammas, electrons, protons, alphas, heavy ions, and neutrons in a single system is very, very difficult. Hence, we have to use a intelligent system to detect all of them, or intelligent system to the specific particles with a wider range of energy. Then we have to go with a combination of the system, like not a single system what we are using in our laboratory, like a GM counter or a scintillation counter. It is not possible to use them because space has another constraint. This volume, mass, and power. They have given a amount. The budget is called as a budget: volume budget, mass budget, and power budget. Within that budget, we have to choose a particle system and a detector system and address the space mission definitions. Here, these are two systems I work. This is a combination of, this is a electron detector system. This is a crystal system, high density crystal we use, and there is a silicon detector is glued on this. And I will show in the coming slides how the detector system work with the different techniques. Here is one of the detector system. Is used in ExoMass. What I mentioned, I started my career with ExoMass. It has a 4 silicon detector with 5 micron thick, and one is top, and 3 are sitting here very close by. And the idea was detecting this using this detector system for charged particles and neutral particles as well, by a technique called as a anti-coincident technique. Okay, I will show in the next slide. Here, the same system we adopted in the Chinese dosimetry unit. That's a lunar lander neutron dosimetry. It was launched in January 2019 and landed on moon and worked very well. And it has a extended version of this IRS. IRS has a 44 detector system. It has a 10 detector system, and detection capability is increased to the higher than the what I have shown in the earlier system, and also it has a capability of detecting the thermal neutrons and fast neutrons and gamma particles. But the efficiency is less, but okay, it has a very vast all kind of detection of all kind of particles in wider range. This is electron system and this is electron system, and this is the detector system, and this is a moon lander of the this mission. Now I will go to the detector system. What I mentioned, it has 10 detectors. We call it as A to J, and we make it as we arrange the geometry such a way that it has to cover a wide field of view and a large amount of charged particles. Here detector A is segmented into 2 and B, C, D. Here 3 detector systems very close by, and E and F, and there is a gadolinium foil here at G and H. In between there is a gadolinium foil, and okay, there is anti-coincidence detector system. These detector systems are 500 micron thick, and gadolinium foil is here. The thicker one is 250, and in between the detector system there is a gadolinium foil with 20 micron. Okay, the purpose of gadolinium foil is to detect the thermal neutron. Okay, I'll show you the next slide. Here, but how we are determining the charged particles, especially heavy charged particles. Again, it's a energy loss mechanism, what I have discussed in one of the slide. That's a Bethe block formula. Here the detector A, B, C, D. Here we will collect the sum of the energy detected and the energy loss in the detector, in the first detector, and the sum of the energy. If you plot like this, means first detector and sum of the energy. For example, if you take A and B, then what is the amount of energy is lost in A, and A and B sum of the energy. If you get a nice plot like this, it's a bracket, then here like this, then if you project it on the x-axis, you will see the particles, energy, and you can identify which kind of particle as well. If you extended similar to the AB combination, ABC combination, ABCD combination, we can increase the energy of the detection of the particle by increasing, because it's additional masses. If you added every detector, then you are adding a 500 micron thick of the silicon detector. Okay, that's why its energy is increasing. Hence, we are detecting and covering a vast energy from 40 to 130 MeV per nuc, means MeV per nucleon. And if you multiply with the ion jet, means atomic energy, atomic number, then you get the total energy of the particle. Okay, then the thermal neutron. This is the main I would like to discuss here. Here, what I said here, it has a capability of detecting the thermal neutron. Why the thermal neutron? This is a question to implement this technique. The idea of detecting thermal neutron is to understand, to identify the water content of the soil, water content on the moon soil. Hence, why it's how the thermal neutron gives the water content of the new soil. What I have shown here in the one of the slide, we can detect the neutron by using the heavy water or hydrogen-rich material that will give the signature of the water. Or signature. I mean, if the neutron, we can easily stop by the heavy hydrogen-rich material. Water is one of them. Hence, if you find the thermal neutrons are generated, means when neutrons are when fast neutrons are going through the high rich hydrogen material, then they are they accelerated and they loses their energy. If you categorize the neutrons, fast neutrons, slow neutrons and thermal neutrons of energy having a 25 milli electron volt, when they least their energy is reduced to the thermal neutron, and those are determined by through the technique. It means that there are some water molecules present in the soil. This is the idea behind to determine to use this technique to understand the water soil in the moon surface. Here, what happens? Why you use this technique? Here, gadolinium. I will show. Here, these are the peaks. Internal conversion electrons. I will mention why we have used this technique. I will show here, because gadolinium we have used. It has a high cross section of the neutron, especially the thermal neutron. Because of that one, what we did here, we stand with gadolinium between the two detectors. If a thermal neutron enters into the system, then it is absorbed by this gadolinium. Once it's absorbed, it is generating the X-rays. That's called as internal conversion electron. What I have shown here. These are the internal conversion electron peaks. If you see the internal conversion electron peak, this is the indirect way of determining this thermal neutron. Once we determine the thermal neutron, then we can say that there is so much of water content on the soil. This is the idea behind using this technique. This again, why I mentioned why internal conversion electrons, because these electrons are having a sufficient energy to detect. If you go with the detector technology, all detectors having a very thin layer of silicon oxide that is not actually is not using for that thin layer. What happens? It block the scattering light, and it good for the detector system. But this amount of energy of X-ray it's easily penetrate through this one, and we can easily find out these energy X-rays in the system. And finally we can say that this is the intensity of the X-ray. Then so much of thermal neutrons are present. This is not from the our experiment result. It is from the for explanation purpose in the laboratory. Here it is calibration results. What we have done after designing and build the instrument, we have to calibrate this one and identify the calibration factors. That's why we did this calibration in the neutron source facility and understand the all peaks and the calibration factors. Then those calibration factors are applied in the space when we are identifying these things, these peaks. Then just extending the its capability of understanding and detecting the gamma and fast neutrons. Here in the detector system BCD, BC is segmented into three parts. One is the inner part. There's a ring and the outer part. What happens here, if it have charged particles, this is for the fast neutrons and gamma, cannot the thermal neutron. Thermal neutron technique is different, and fast neutrons and gamma technique is different. Here, only we consider a true counts. There is no count in the detector B, and there is no count in the detector D. Only a charged particle a particle is appeared in the central segment of the detector C. Then only it is considered true count, and it is a neutral particle. Either it is a gamma or it's a fast neutron. Again, this is analyzed by the pulse shape method, and we will find out it's a gamma or fast neutron. Hence, I can say this detector system is it can detect charged particles, neutral particles. Hence, it is a nice detector system. But efficiency is if you go to the high energy gamma, its efficiency naturally decreases because of the gamma intensity is increases. Gamma energy increases. Interaction probability in the material decreases, because here the thickness of the detector is same, is not varying. But if you go to the spectrum of the gamma energy, then so lower energy is higher the detection probability, and the higher energy so lower the detection probability. Then just summarizing the results. This is one of the LET spectrum. of this system, the LND. It's a lunar neutron dosimetry. Here is this charged particles. We have seen this is a energy converted into water, this LET, and we have seen a nice peak, and there are minor peaks here. These are the different ions we will see, but it's not so clear here. But it has given a very nice spectrum of all the charged particles. This is a combination of several detectors. Means what I have mentioned: A plus B, A plus B plus C, A plus, okay, combination of 1, 2, 3, 4, 1, 2, 3, 4, 5, and we can extend the energy of the particle. Then here, this is a dose estimation in different detector system. Here there are different doses, neutral doses, charged particle doses in different dose system, different techniques, and thermal neutron doses. In charged particles, it's considered as a sum of the detectors. Neutral is only the neutral is only the C detectors, and thermal neutron in the detector. Sorry, here, okay, detector E and F and G and H, and these are giving the thermal neutron doses. And here the total dose is measured here, and there was a background because the spacecraft has a thermal some RTGs or RHUs. Those are emitting some radiation, especially neutrons. That's why the background, this is the background, and after detecting this background, okay, so it's estimated that this is the final dose seen in the detectors in the system per hour. If you summarize them, comparing with the other system, other places, when comparing this LND result with the Mars and ISS and Earth surface, this is from the MSL RAD. This is another instrument is developed by the University of Kiel. And it's a NASA mission. It's landed on Mars in 2016, I guess. Then 2012. Then okay, they observed and presented the result in in Science journal. Then it's a moon. What we have discussed. This is also presented in the Advanced Science Advance, and it's understood that it's 57 microsievert per hour. And this ISS Dostal is again developed by the Kiel University. This is in the ISS, and from the ISS data, it shows that okay, it's radiation dose is 22 microsievert per hour. If you go to if you monitor or if you observe or detect this Earth surface radiation dose, generally we will see around 1 microsievert per hour. Especially here, I collected from the internet the Kerala coastal, comparing to all these things, different environment. From this, we see that the radiation dose in Moon is very high. Then okay, so Mars, then ISS and Earth. ISS is around 250 kilometers. If you go to the Mars, we know Mars does not have a powerful magnetic field. Moon does not have a magnetic field, and there is no atmosphere. Mars has atmosphere, and also it's far away from Sun. And okay, so because of the it's far away from Sun, the radiation dose is less. Here, Moon there is no magnetic field and there is no atmosphere. Hence, the radiation dose is much higher. And ISS, okay, even though it's in Earth atmosphere, and okay, no, it's just above the atmosphere, but even though it's within the radiation belt, but okay, because of this atmosphere is not shielding, hence it is showing some nearly 20 times more than what we are seeing on the Earth's crust. With this, okay, I can say that what we have done, what we have discussed, we know, okay, what is a space radiation, how it is important. I forgot to mention, I think we might have heard in the news a month ago, there was a glitch in the Airbus 320. Okay, that's due to the cosmic radiation. Okay, hence the understanding the radiation is very important. Because of that one, okay, they landed all the Airbus 320 flights grounded to understand what happened to their electron system. Hence, it's very, very important to understand the radiation environment which around us. And here I have shown some detector techniques. It is an art because there are several kind of particles, and energy range from few EV to 100,000 of GeV. Hence, we have to have a very specific and combination or of detector system to detect and understand the type of the particles. And if you compare to the space and ground, space has some limitation because of lifetime and there is no repair option. Hence, we have to have a very defined program and planned program and intelligent mission to send to the space, because there is no repair option. Then what I have shown here in presentation, the detector systems are for the space application. They are capable of detecting from few keV to GeV particles, charged particles as neutron, and those are published in the journals. From this, I'm concluding. If you have any questions, please let me.
Thank you very much for a very informative talk. Now, would you take a few questions from the audience?
Yeah, please.
Professor Rudaswamy, you want to ask any question? Okay. Rudaswamy, you can unmute. You can unmute and ask your question.
Thank you. Thank you, sir. Professor Kulkarni, nice presentation. I have small 3 questions.
Please, sir.
First question, what is the reason for the existence of 90% protons in cosmic ray particles? How galactic and extragalactic regions are classified? What is the reason for neutrons having more degree of penetration compared to gamma or X-rays? So these are the 3 questions, small questions.
Protons are the smallest particle. I mean, I can say it's a nucleus is consisting of the protons and neutrons, because protons are there's a smallest charge positive particle, and I mean and easily abundable. They are easily generated in the solar system, stars, and also in the galactic process like a supernova. That's why that's easy to produce them. That's the reason the proton is abundance is very, very high when compared to the heavy charge particles. Heavy charge particles, they need, for example, if you take a star like sun like a star, then it's rich in hydrogen. Because of this fusion, end product is iron. It cannot go beyond that one, but it takes so many years to reach that state. Then but the protons are when they are ejected, then the plasma is consisting of protons and mainly protons and helium and electrons. And second one, you asked for the neutron, is it?
Yeah,
galactic and extragalactic.
Neutrons. So origin of neutrons.
Origin of neutron is it's again it's a fission process. Sometimes there are neutralization of the protons also happens if it is a proton loses its energy and in the space, either it is in the intergalactic or galactic, where it may be, then it may be become a neutral particle. This is one thing. Another question is,
what is the reason for neutrons having more degree of penetration compared to gamma or X-rays?
No, neutron is a neutral particle. Gamma is again it's the interaction type of interaction. Gamma is only interacting with the electrons, but neutrons are only interacting with the nucleus. It's because of its heavy particle, and when it head-on collision with the nucleus, then it loses its energy. But gamma is not like that. Gamma is it's interacting with charged particles, orbital electrons, as well as the it's electromagnetic radiation. This mainly it's the nature of this types, electromagnetic radiation, and it's just a particle without any charges.
Okay, we'll move on to next question.
Thank you. Thank you.
Paniveni, would you like to ask your question, please? Please.
Thank you very much for the very interesting talk, sir. I have very basic questions. I would like to know about the kind of energy associated with this thermal neutrons that you said would be useful for detection of water content in this space missions. So, what would be the general kind of energy associated
Energies.
with
It's
neutrons?
several
Thermal
MEVs,
neutrons.
several MEC to MEV to thermal neutron. Thermal neutron is defined as a 25 electron volt. It's called they defined as classified as ultra fast, slow neutron and thermal neutron. Like that. Okay, so in the MEVs, okay, it's the very few. Okay, higher MEV is ultra fast and fast neutrons, and okay, slow neutrons in terms of MEV KVs. Then okay, if you go to the less than KVs, the epithermal and thermal neutrons. Okay, why we are okay? So here the idea is to using the thermal neutron means we have used the gadolinium. Gadolinium is one of the substance has a high cross section of thermal neutron. For example, in a nuclear reactor, they are using a boron. Boron it has a high neutron cross section for neutron absorption to control the neutron number for that's called as control nuclear reactions. They control the neutron number using boron. Here, its idea is to absorb the thermal neutrons and they emit the X-rays and detecting these internal conversion electrons and by this indirect method, okay, we understand how much water content on this soil.
Okay, we move on to next.
Another very simple question is, what is this ExoMars mission you said? You mentioned about
ExoMars is it's a Mars mission. It's a ESA mission, European Space Agency mission. Started 2008 or so. I joined as a lead scientist for that instrument. IRS is a energy and radiation sensor, but unfortunately, it's not. Continue because of some regions conflict between the Ukraine and Russia. Okay, several things. Okay, I'm sorry, I don't want to say.
Okay, that's okay. Any other questions?
Thank you very much.
Okay, I have a very simple question that you mentioned earlier that there are two radiation belts around the Earth. I thought there was only one belt. Are there two belts around the Earth? Is it?
Yes, several, sir. Actually, no. Okay, yeah. There are They mainly they mention as a two belt. Okay, there are small fine structure in the belts. Okay. Fine structure. There is a one mission called I did not mention here. There is a one mission called as a Val Allen belt. Okay, the lead scientist, his name is Shrikant Kanekal. He's a NASA scientist. He is leading that project. He is from also Bangalore University. It's a beautifully they mentioned how the belt are formed, how they are leaking taking place when the solar activity happen, when sun is quiet, how the structure of the belt. Okay, that's a beautiful. There is a videos also one can find in the YouTube.
Look it up. Yeah. What about the radiation levels in some of the satellites? They are also sent around the Earth. You mentioned only ISS and Moon and Mars. Even satellite communication satellite, big satellites are there. What kind of radiation dosages they are receiving?
Yes, sir. These are the things. Okay, in here, Mynaric, I am one of the person involving that one. We will. Okay, actually, that's why it's the popular the low Earth orbits and geostationary orbit. Low Earth orbit is within the 1,000 kilometers because this is just below the inner radiation belt. The next level is MEO. MEO, no one is going for because of high radiation, trapped radiation. They go to the GEO. GEO is 36 kilometers 1,000. Okay, there is no radiation belt. Okay, for these things they are taking care of the all the shielding, especially for example GEO is a single event effect is very very predominant because of the high charged particles. This is a galactic event, high energy particles and heavy particles. If you come to the LEO is total dose effect is very very important. Okay, that's why we are considering the shielding. Shielding means depends on the mission lifetime and how much in which altitude and which inclination it is present in the satellite. On the basis of that, we are using the shielding material, either aluminum. If it is not aluminum sufficient, then we go with the high jet material to shield the electronics.
Okay. Any other questions? Anand, would you like to?
Sir, actually, about that with respect to that 11-year solar cycle, normally we have seen many upsets happening in any of the electronic circuits.
Yes.
So, what is the minimum energy with which you find a CU on a chip, particularly in our geosatellites? Basically, I worked in geosatellites. We have seen many kind of signatures, slopes of some of the actuators like gyroscopes and other things.
Okay.
Some other things. So typically, what is the
Okay, let him answer because now again we are running out of time. Another 3
minimum
minutes
energy
left.
level we expect SEU?
Yeah,
Okay.
let him
Actually,
answer briefly.
yeah. There are two phenomena. You already mentioned the SEE, single event effect. Single event effect is okay, depends on the destructive or non-destructive, means software effect. Generally, you come if you see the device data sheet, they will give you some guarantee, means radiation tolerant or radiation hardened. They will test with the xenon ion with LET with 65 MeV centimeter square milligram. Those kind of, okay, if you use that, can survive for your mission lifetime. Maybe GEO generally is a plan for 10 years because it's a expensive mission. And okay, Leo. Also, we are okay. Everyone is Leo. They are planning for a 35, 36, up to 40 LET units, means MeV centimeter square milligram. Because what happens if you see the spectrum, if you go to the individual level spectrum, you will see a dip in at 29 MeV centimeter square milligram. It means that, okay, so beyond that one, there is a single event effect, but abundance is high energy, heavy charge particle. Abundance is less. It means that we can calculate the cross section of these events or effects. The basis of that one, we can see that with survive for us 5 years or 7 years or 10 years. That way we are calculating, and okay, one can plan for the mission, depends on their plan.
Okay, thank you very much. Again, we are facing the same problem as we faced earlier. The meeting is going to end automatically. So before that, I would like to thank all the participants. I'd like to thank our speaker, Dr. Kulkarni, for taking out the time at this hour and telling us about the latest developments in the detection of radiation from space. Thank you very much. I would like to also thank Dr. Raghavendra for providing the link regularly for conducting our meetings, and thanks to S.V. Raman for broadcasting this meeting on live on YouTube. So he's actually reaching out to so many students all over the state. So thanks to him for giving us the YouTube link. So before we close, I'd like to thank you all of you again, and mention that again next week at the same time we are having another meeting, Zoom meeting. Please join us. So we'll continue our journey of learning for a long time. Thank you very much. So thanks you, all of you. Now we are closing the meeting, and otherwise it will close automatically within 1 minute. Okay. Thanks a lot. So we'll meet next week at the same time. Thanks, Dr. Srinivas Kulkarni.
Okay. Thank you, sir. Thank you very much for giving an opportunity to present my work in this Karnataka Physics
Many
Association.
technical issue matters that we are not aware of usually. So we learned a few things about the detecting